Moving on to our next video here, talking about stationary points. So we're going to be building on the things we've been talking about in the previous sections. Specifically, we're going to find, interpret, and classify points where the derivative of a function equals 0 using a variety of methods. So first, a definition here. When we refer to this idea of a stationary point, that's just any point where the derivative equals 0. Now that point, it could be a local maximum, meaning if the function does something like that, that would be a local maximum. It could be a local minimum, like that would be a local minimum, or a stationary inflection, which we'll talk about moving forward here. All right? So that's what we're focusing on, those points where the derivative equals 0. Now, like I said, there's a couple of different things that it could be. Now, we could have what's referred to as a global minimum down here, point A. Meaning the function never goes below that point. Obviously, we have a restricted domain on this function here that we're really focusing on here. We could have a local maximum right here at point B, a local minimum, as you see on point C, a global maximum, the highest point on the function up here at point D, and then we have some other things going on. All right, so that's what we're talking about here. Let's spend another few moments talking about stationary points of inflection. All right, so it says it's not always true that whenever we find the value of x where the derivative equals 0, we have a local max or a local minimum. For instance, if we have f of x equals x cubed, we see f prime of x equals 3x squared. And obviously we know that f prime of x equals 0 when x equals 0. But when I look at that function, it's going along here, I get to 0. And that's not a local max or a local min. It's just kind of like a stop in the road, okay? We refer to that as a point of inflection or a stationary inflection because what's happening is that the curve is changing its curvature or it's changing its shape. So if you think about that, as I go up here, I'm increasing, my function is increasing, but it's not increasing as rapidly anymore. At the beginning, it's increasing very rapidly, and then less rapidly, until I get to a point right here. And at that exact point, it's not increasing at all at that very instant. But then it starts to increase more and more rapidly, and starts to increase more and more rapidly as I go out there. So at that point there, x equals 0, we see the shape where the curvature is changing at that point. Now, what do all of these look like as far as the sign diagrams of the derivative function? As we look at this function up here and the sign diagram below, if we look at this local maximum right here, well, the function's increasing prior to that point, but then the function begins to decrease. So we see a change in the sign of the derivative at that point. The same thing occurs at this local minimum here. It is decreasing before positive 1, but then I get past positive 1 and the function starts to increase. So the derivative is positive again. But when I get to x equals 3, that stationary point of inflection, it was increasing before 3, it's still increasing after 3. So that stationary point of inflection does not show a sign change in the derivative function there. And that's how you determine whether it's a local min or max or a stationary inflection. This chart summarizes everything for you. If you go from positive to negative, you're going to have a local maximum. If your derivative function goes from negative to positive, you have a local minimum. If it was positive and it stays positive, stationary inflection. If it was negative and stays negative, also stationary inflection, excuse me. So let's put that to use here, and we're going to focus on this function, f of x equals x cubed minus 3x squared minus 9x plus 5. We'll start as we have been all of these problems by finding the derivative function, 3x squared minus 6x minus 9. We want to have an idea of where the zeros are for this because that's going to be our key points that we can find and classify. So just pull out a 3, and now I have x squared minus 2x minus 3. That's factorable. I can get x minus 3 and x plus 1. So that means x equals negative 1 and positive 3. so I can make my sign diagram. And all I have to do is figure out what the signs are in it. And again, I'm becoming a broken record, but we're plugging that into the derivative function. So if I picked a point, say 0, if I plug in x equals 0 into the derivative function, I clearly will end up with a negative value. If I pick the point out here on the right, like x equals 4, I'm going to end up getting a positive value. If I pick the point like -2 over there on the left, I'll get a positive value. So what's happening? As I go along this function, I'm passing through this point where the derivative equals 0. I'm going from positive to negative, so my sign changed. So the function was increasing, then it started decreasing. That means that I have a local max at x equals -1. Keep going, keep going, keep going. What am I seeing? Okay, my function is decreasing, and then all of a sudden I get to x equals 3, and my function starts to increase. That means I have a local minimum at x equals 3. And that's it. Those are the only two stationary points that this function happens to have. And you can see it when you look at the graph of it. We see here we have a local max and a local min, and that's it. That cubic function is pretty easy to work with. When we look at this one here, a little bit more challenging. When we look at it, we see a couple things going on here. If we wanted to figure out where the position and the nature of these stationary points were, we need to find our derivative function. So if I see that I have that y equals, let's go ahead and write out the product rule. We're going to say that u is x minus 2, so u prime is 1. V is e to the negative x, so v prime is negative e to the negative x. And now we could find f prime of x just by plugging in e to the negative x plus x minus 2 times negative e to the negative x. If I wanted to do a little bit of simplifying here, I could pull out an e to the negative x. Now I have 1 minus, let's see, I still have that negative over there, x minus 2 times negative 1. And that ends up becoming, yeah, my parentheses match up there. That ends up becoming e to the negative x of 3 minus x, or 3 minus x over e to the x. Now, we care when this is going to be equal to 0, so I'm really looking at 0 equals 3 minus x, or x equals 3. So this sign diagram only has the one point there, and if I plug in points, if I plug in, say, x equals 0 into the derivative function, again, this is the most simplified form of that derivative function there, I'm going to have a positive value over here, negative value over there. So the function's increasing and it's decreasing. That means I have a local max at. Now, because it asks for the exact position, I'll need the y value as well. So the local max is at 3, comma. And then if I were to plug in x equals 3 into the original function, I would end up getting the y value of 1 over e to the third. So that is that for that particular problem. We're going to look at just one more example to talk about classifying these points here. And this one's a little bit different. It says find the greatest and least value for this function from the interval -2 is less than or equal to x is less than or equal to 5. Now, what that means is there might be a local min or a local max that is one of these values, or there could be one of the endpoints that's the key. So what we're going to do, the first thing is I'm going to go ahead and find that derivative. And I'm going to say, all right, that's 3x squared. That's going to be minus 12x. And then I want to know when that equals 0. Pull out my 3x. Now I have x minus 4. So the x values are 0 and 4. Make our sign diagram. Going quickly here because I think you guys got it at this point. When you plug in, you have positive, negative, positive. Okay, so Now, the next thing I want to do is I want to make a bit of a chart. Okay. Now, the x values. The x values that we're interested in, I'm going to go from smallest to largest. I'm going to look at -2 first, because that -2 is an endpoint. I want to know what's going on there. Then I'm going to check what's happening at 0, because that was one of our values that we were interested in. I'm going to look at 4, another value I'm interested in, and then I'm also going to look at 5, which is the other endpoint. Okay. Now, when I think about what's going on here, I say, what kind of point is it? So type of point. So at -2, that's an endpoint. When I look at x equals 0, well, my derivative went from positive to negative, so I was increasing, and then I started decreasing. So that's going to be a local max. And when I'm at when I'm at positive 4, my derivative function went from negative to positive, so I was decreasing, and then I started to increase. That means I have a local min. And the 0.5, that's also an endpoint. Okay. So now I need the y value that goes with each one of these, and I get that by plugging into the original function. So at -2, I have -27. At 0, I have 5. At 4, I have -27. And at 5, I have -20. So when it asks for the greatest and the least values, well, the greatest, and we're talking about the greatest y value, the greatest is at the point right here, 0, 5. As far as the least, we have 2 of them because there are 2 -27s. So I'll list both of them there. I'll say that I have -2, -27, but I also have the point 4, -27. Okay, so that is going to be that. And you could look at the curve and kind of see that that's exactly what is going on here. When I have the point -2, I'm at the same y value as when I'm at x equals 4. And yes, 0, 5, that is the maximum or the greatest value for that function. So that's it there, just talking about what could be happening when the derivative equals 0. As we see, it could be a local max, could be a local min, or could be a stationary inflection. And that's it. And next time we'll come back and spend